Radiation is energy in electromagnetic form and is one of the most common environmental exposures. We're exposed through natural and human-made sources. Some radiation sources are considered background, while others are associated with radioactive materials or activities such as sunbathing, flying, and medical procedures. Radiation can also be an occupational hazard. Radiation is a core topic in environmental public health because of its ability to cause damage to cells and to DNA. We haven't known about radiation for all that long, just over a century with the discovery of the X-ray in 1895. Advances in deducing atomic structure followed in the early part of the 20th century. The first self-sustaining uranium fission was demonstrated in 1942, and the first nuclear reactor produced electricity in 1951, paving the way for atomic or nuclear energy, which is an important part of the global energy mix today. The year 1945 saw the detonation of the first atomic weapon in Hiroshima and Nagasaki. Here are the basics of radiation. The nucleus of an atom has protons and neutrons. Some combinations are stable and some aren't. Unstable combinations will transform or disintegrate to achieve a stable state. In the process, radiation is propagated through space via photons. Each has a specific wavelength, frequency, and energy. As the wavelength shortens and the frequency increases, more energy is released at close range, which is potentially dangerous to living things. Ionizing potential refers to whether the radiation contains enough energy to ionize atoms or to strip away their orbiting electrons. The resulting energy transfer can result in chemical and biological changes in cells that can harm health. Moving from the bottom of this figure to the top, the radiation types are arranged in order from containing the least energy to the most energy. Again, note that non-ionizing sources contain less energy than ionizing sources and do not contain sufficient energy to ionize matter. Let's take a look at each of these radiation types, starting with the low-energy sources at the bottom. It may be useful to have your book open to page 605 while you review these slides. Electric and magnetic fields are usually coupled and referred to as electromagnetic fields, or EMFs, contain the least amount of energy. These are all around us. They're present in thunderstorms, power lines, household appliances, video display tubes, MRIs, and motors. Some occupations with high exposures include power line workers, welders, and machine operators. While EMFs and adverse human health effects are not well linked, exposure limits exist for both workers and the general public. People with pacemakers should avoid stronger sources of EMF, such as transformers. These strong sources should be posted. Moving up in energy, we have radio and microwave radiation. Common sources include radar, TVs, radios, cell phone and towers, and microwave ovens. The biological effects appear to be primarily thermal, as they can penetrate deeply and burn dermal and subcutaneous tissue. There may be other effects, but the data are limited, which is why the question of whether cell phone use increases the risk of cancer remains unknown. Protections require proper design and shielding of the sources and exposure limits, which are based on the amount of radio frequency energy absorbed by weight. Moving up the textbook figure is infrared radiation, which is experienced as heat. Sources include the sun, fire, hot blacktop on a sunny day, heat lamps, furnaces, welding, and other occupational sources. This type of radiation can cause burns of the skin and the eyes, resulting in cataracts of the lens of the eye. The lens of the eye is considered more vulnerable because, unlike the skin, it lacks heat receptors and is not able to dissipate heat. Protections include limiting the duration of exposure and shielding from the source. Engineering controls may be indicated in occupational settings. Visible light, as its name implies, is experienced as light. Sources are the sun, lasers, welding arcs, and tungsten filament lamps. Too much light can result in retinal injury, while too little can result in eye strain and seasonal affective disorder. Laser radiation can cause injury to the lens, iris, cornea, and skin from thermal effects. Protection efforts are focused on industrial application of high-intensity sources such as lasers, and may include engineering controls, training, supervision of workers, and PPE such as eye shields. Ultraviolet light spans the non-ionizing and the ionizing divide, as it's non-ionizing at its lower frequencies and ionizing at higher frequencies. The primary source is the sun, but there are other human-made sources such as low-intensity fluorescent lamps and high-intensity tanning beds. There are also multiple occupational sources. Although there are many harmful effects, ultraviolet radiation is also essential for the synthesis of vitamin D. Ultraviolet radiation is subdivided for convenience based on the bands of the spectrum into UVA, UVB, and UVC. Although UVA is more intense, UVB plays a larger role in skin cancer. Protection of the public includes limiting exposure, such as sitting in the shade, and protection through windows, clothing, sunscreen, and sunglasses. Occupational protections typically include engineering and administrative controls. The Earth's stratospheric ozone layer provides some protection from ultraviolet radiation, but has been compromised by the use of chlorofluorocarbons and other air pollutants, resulting in greater amounts of UV radiation reaching the Earth. The Montreal Protocol is a successful piece of international policy that has decreased the use of these air pollutants, resulting in some repair of the ozone layer. This policy is credited with averting millions of cases of skin cancer each year. The three main radiation types that make up ionizing radiation are X-rays, gamma rays, and cosmic ray radiation. They all contain sufficient energy to break chemical bonds that give rise to ion pairs and free radicals. They all contain, before we move on, let's cover a few basic definitions that are important to understand ionizing radiation. The text describes radioactivity as spontaneous nuclear transformations that result in the formation of new elements. Radionuclides are radioactive elements which can be quantified by their transformation kinetics, including activity and half-life. Half-life is the time required for half of the radioactive atoms to decay. Activity is the rate of transformations over time and is a measure of how radioactive something is. Radiation exposures are divided into external and internal doses. An external dose comes from outside the body, such as a chest X-ray. An internal dose occurs when radioactivity enters the body through inhalation, ingestion, or absorption, such as inhalation of naturally occurring radon gas inside a home. Ionizing radiation comes from both natural and human-made sources. Natural sources include cosmic rays from space that hit the Earth's atmosphere, where they interact with atoms like nitrogen and oxygen. People who live at higher latitudes and altitudes receive more cosmic radiation. Flying and space travel also increase cosmic radiation exposure. Terrestrial radiation is emitted from some radioactive minerals in the Earth's crust, such as uranium and radium. This varies substantially by geography. Radon is a colorless, odorless gas that results from the decay of radium, a radioactive element found in nearly all rocks. Inhaled radon decay products comprise over 2/3 of the natural background radiation dose. Some radiation exposure is from internal emitters, notably potassium. Potassium is an essential element and present in many healthy fruits and vegetables. Potassium has a very long half-life, so this dose is small and unavoidable. Human-made sources include consumer products such as smoke detectors, granite countertops, some ceramics, and cigarette tobacco, which is delivered directly into the lung tissue of a smoker. Medical procedures such as X-rays and especially CT scans contribute about half of the human-made dose on average, but can be substantially more in people requiring repeated medical procedures. Finally, nuclear power plant accidents have resulted in exposure, most notably 3 Mile Island in Pennsylvania in 1979, Chernobyl near Kiev, Ukraine in 1986, and Fukushima Daiichi in Japan in 2011. The highest exposures were from Chernobyl. Amazingly, most people in the Northern Hemisphere were exposed to some degree. Ionizing radiation affects cells in two main ways: genetic effects through DNA damage and somatic effects by affecting cell survival. Check out the first video in the class notes for a more entertaining explanation of these two main mechanisms. Ionizing radiation causes three main types of health effects: acute effects, carcinogenic effects, and effects on the embryo and fetus. The tissues that are particularly sensitive to acute effects are skin, bone marrow and lymphoid tissue, intestine, gonads, respiratory tract, and the lens of the eye. Cells that are dividing rapidly are particularly radiosensitive. Whole body radiation can result in radiation syndrome or radiation sickness, which starts with more generalized symptoms of malaise, anorexia, nausea, and vomiting, followed by an asymptomatic latent interval, a main phase of illness that can take on one of four forms, which are hematological, gastrointestinal, cerebral, or pulmonary, and finally either death or recovery. By contrast, localized radiation injury evolves more slowly and produces fewer symptoms unless the dose is very high. The carcinogenic effects of ionizing radiation have been described through epidemiologic evidence generated from occupational studies. The tumors are typically detected only following large doses of radiation, take years or decades to develop, and have features that differentiate them from other tumors. Other epidemiologic observations include cancer occurrences among atomic bomb survivors, radiotherapy patients, and people living downwind of nuclear test and accident sites. Finally, the embryo and fetus are highly susceptible to radiation. Notably, it can cause a killing effect during pre-implantation and malformations during organogenesis. Possible pediatric outcomes of prenatal exposure to ionizing radiation include increased risk of cancers and a dose-dependent loss of IQ. Radiation protection differs by whether the source is internal or external. Internal radiation protection methods aim to prevent exposure and include engineering controls to confine air or prevent ingestion or skin contact. PPE is used as a last resort, since it's the easiest intervention to ignore. Prevention methods for external sources are in order of preference: eliminating the source, engineering controls to minimize exposure time, maximize the distance from the source, and finally shielding. All radiation exposures, whether in occupational or medical settings, should be kept as low as reasonably achievable. Radiation exposures are only justifiable if there is sufficient benefit to those who are exposed. Most risk assessments for low-level radiation assume a linear increasing risk with increasing dose. See the video in the class notes for more on this. Epidemiological data suggests children and people with certain hereditary disorders are more susceptible to certain types of radiation-associated cancer. I'll end with a family photo of a couple with very different radiation prevention practices. Public health efforts to minimize radiation exposure must occur at multiple levels, from international treaties to engineering control for home and workplaces to influencing individual behaviors.